Hello, hello. Here is our recap of the lab. Do not overthink this first part. I'm asking you to illustrate a 20 Newton force on this graph. I'm not asking you to illustrate an object moving. This is a graph that shows you how force is changing or not changing with distance. In our case, it's a 20 newtons force applied to an object, remaining the same. 20 newtons is the value of it. And the distance traveled by the object, or displacement, to the right here, 4. That's all I'm asking you to do. So we're illustrating a 20 Newton force applied to an object over a distance of 4 meters. Both of them are to the right. Both of them are positive. Then the next thing I'm asking you to shade in the area under the graph. So when we talk about under the graph, we mean between the graph line and this axis horizontal. That is what is meant by the area under the graph. So the area under the graph will be all of this, basically a rectangle. The area of a rectangle, 20 times 4, and unit-wise, it's newtons times meters. So that's 80 newtons times meters. If we were talking about torque, we could leave it like that, but for our purpose, we're going to say this is 80 joules. My next question is, so use the formula for work to calculate the work done by the 20 Newton force over the 4 meter displacement. Again, we said both of them were to the right. Formula work equals force, displacement, cosine of theta between the two of them. If they're both to the right, then that's a 0, which makes the whole cosine of 1. So I can just ditch that. If the force is in the direction of the displacement, just multiply that force by that displacement. The force was 20. The displacement was 4. What do you know? 80 joules. 80 joules of work. The area under the graph is 80 joules, and the work done by the force is 80 joules. Make the connection. The area under the graph, force versus displacement, represents the work done by that force. Important. By the force. Not on the object by some other force, but by that force that you applied. So observe elastic spring. So make sure you clicked energy. So force plot, what you can see also is if I change the spring constant, that kind of changes the slope. Interesting, huh? So what I need you to click is also energy plot, because after we looked at the very beginning at how if we have a force that is constant of 20 newtons is applied over 4 meters, if we draw that straight line and shade the area under, that area would be equal to the work done by the force. Now, in this case, we are showing the potential energy, and that is potential energy elastic. That is the energy of the spring. So look what they're doing. They are showing you that triangle, and you can see right here, they show it's going to be a triangle. You can also see that area of the triangle grow with displacement and with force. And on the left right here, you can also see that that bar is increasing with displacement. So the greater you displace the spring, the greater the force you are applying and the greater energy you are creating. Now, mind you, you are doing positive work. You are pulling the spring to the right and you're doing positive work on it. Displacement is to the right and force is to the right. They are showing you the applied force, and this area under that graph represents the energy of the spring. Now, if you get the values, you can see that it's 50 joules, and the area of this triangle, this right here is 1 meter, this is 100. This would be my base, and this would be my height. The area of this triangle will be 1/2 1 multiplied by 100. 50 joules right there. And if I go and compress it, both of these guys are now negative, and the energy is still positive, because this is going to be 1/2 of -1 times -100. Still positive energy. Above or below, we end up with a positive energy. And that energy equals the area of the triangle that they are nicely shading for us. There you go. Remember Hooke's law. Hooke's law teaches us that force of the spring equals negative kx, where k is the spring constant, and that negative sign is directional because they're in the opposite direction. The force of the spring and the displacement are in the opposite direction. And that is what some forgot when they were drawing the graph. The graph that they showed you had this slope. This was the applied force. I'm asking you to illustrate the force of the spring because the formula is negative kx. That means that for the positive displacement, which is right here, anywhere right here, the force is going to be negative because they're in the opposite direction. For a positive displacement, you have a negative force from the spring. So this right here, let's say we stopped at 1 meter and our force is negative 100 newtons, then the slope of this graph will be negative 100 divided by 1 meter. It's going to be negative 100 newtons per meters. That is the slope of that line. So the slope of the line is negative 100 newtons per meter. Force of the spring is negative kx. This is the slope. So if the slope is negative 100 and it equals negative k, then k is 100 newtons per meters. What do you know? You're about to derive a formula. Woohoo! Get excited. Shade one of the triangles in the graph you drew. I did. So this is my triangle right here. And then the area of the triangle, the base is the displacement. This confused some people. I'm just asking you not to write the number, but to write what it was. And for me, that's displacement. So it's going to be change in x. And then the height is the force of the spring. From our observations and conclusions, we said that the area under the graph represents the work done by that force. So instead of area, I'm going to say work by spring will be equal to 1/2. Instead of the base, I'm going to say change in x. And instead of the height, I'm going to say force of the spring. The area that they shaded, remember their graph looked like this. It was a mirror image. And the area that they shaded was over here. And this area was the potential elastic energy of the spring, which is opposite to what this area is. This area is negative, and this area is positive. So if the work done by the spring is negative, then its energy is actually increasing. Here, we're going to put a big fat minus 1/2 force of the spring times change in x. What I'm saying is potential energy elastic is negative work of the spring. Boom. Do you have a minus? Yes. Then incorporate Hooke's law. This force right here, negative kx. So I will continue. Potential energy elastic is negative 1/2. Instead of fs, I'm going to say negative kx times x. Remember, like change in x, just x. It's all displacement. That x in that formula is displacement, so you don't have to do the change in x. So then potential energy of the spring, which is elastic potential energy, minus cancels, x squares, and we end up with kx squared over 2, or you're partial to 1/2, you can do that as well. Which formula does this remind you of? Kinetic energy formula. That is mv squared over 2. And in some of the homework problems in the packet, you will see how potential elastic energy turns into kinetic energy, and you can set them equal to each other. Make a conclusion regarding the value of elastic. Can it ever be negative? No, because even if your x is negative, you like compressed the spring instead of stretching it. When you square it, it's still going to be positive. There you go. I shall see you in class. Thank you for watching and following along.